Hi, this is Matt McCormick. I'm in the philosophy department at the California State University, Sacramento. This is my second lecture for my inductive logic class on the chapters in Daniel Kahneman's book, Thinking Fast and Slow. We're working on chapters 10 through 18, and this is my second lecture on that big block of chapters. So let's talk about what's going on in here in Kahneman. So last time we introduced the book, the section of this book, as Kahneman's trying to answer this question: why is it so difficult for us to think statistically? And the answer, very roughly, that comes out of this big block of chapters is that the sort of quick and fast, hasty part of your judgment system, this thing he calls System 1, employs a long list of heuristics and biases to come up with fast, easy, low effort, generally effective solutions to decisions, but they're not statistically accurate. Okay, so the tools we have don't map well onto statistical reasoning. And we're going to dive into the details here about the cases and the ways in which they deviate and why. How do we think? What does statistics tell us? And where do we sort of mismatch on those? So the last lecture that we did was on this first section, the law of small numbers, anchors, availability bias, emotion, and risk. And now we're going to do these 6 or so entries on stereotypes, representativeness, and base rates through to taming intuitive predictions. That roughly maps on to his chapter headings and roughly captures the topics, the big issues I want to talk about. Now, there's a lot of detail in Kahneman. There's a lot of studies. There's a lot of research. I'm choosing not to talk about lots of the details, and I'm not actually discussing many of the arguments or analyses that he gives. In many cases, I'm highlighting some of and summarizing some of the stuff he does, or I am adding to, supplementing what he did to give us some more examples, or to add on some other material to fill out the picture that Kahneman's given us. Okay, so let's talk about what's going on with what he calls stereotypes versus representativeness. So the bigger issue here, the larger issue in the background, is that we struggle to think statistically. And what happens is that you're a small mind, a small person, a single person with a limited experience and confined things that happen to you. And when it comes to thinking about larger, big picture trends that would require, massive data sampling or massive research and large scale investigation in lots of cases, we just don't have the time, the energy, the tools, the equipment to do it. So, so there may be trends or phenomena that are available or evident or manifest at the larger level if you were to have a sort of omnipresent or omniscient God's eye view of the world. But your sort of hominid journey through your particular set of experiences gives you a statistically distorted picture of the view of the world. But what happens is that we tend to think, very generally speaking, what we can say about this section is that we tend to think of our experience, our little anecdotal, subjective accounts, the stories, the things that have happened to us or the people close to us, as being representative. Representative of the whole, representative of trends, representative of what's going on in the world outside of us, when in fact, they're very often not representative. Okay, so a few terms: the base rate of a property, and Kahneman's going to talk about base rates quite a bit in this section. The base rate of a property in the population is the overall percentage of members of the population that have it. So that's the term we're going to use, and we're going to use that when we talk about Bayes Theorem, because we insert base rates into Bayes Theorem. So you'll start getting familiar with how that language is used in these probability cases. So for instance, the base rate of being a Democrat among Americans is 33% roughly, or a third of a percent, 0.3% of Americans are plumbers, for example. So there's the base rate of plumbers. So were I to ask you, for instance, if I was just to randomly sample some individual out of the population in Sacramento, and then I ask you, what's the probability this person I just sampled is a plumber? Well, if you knew this base rate, you'd say, well, it's 0.3%. The thing is, I can easily coerce or induce you to think that the probability somebody I picked is much higher of their being a plumber, with a few cues, a few sort of causal or narrative hints that will quickly lead you into inflating that probability or to distorting that probability otherwise. So base rates are hard to figure out, they're hard to gather, and it's always good to go look them up and then try to, and one of the background lessons, one of the lessons we're getting from Kahneman here is that we're trying to train our non-regressive and non-representative intuitions to be more in line with actual statistics. The representativeness heuristic then is a way of thinking about the mistake that we typically make. We think that our subjective, anecdotal, small sample stereotype of what a programmer or an athlete or a cop is also representative of the actual class of programmers, athletes, and cops. That is, you've got this causal narrative model in mind of what a computer programmer is, or what an athlete is, or what a cop is, and it may or may not track on the real trends or the real base rates in those groups, but you've got this model in your head, and we'll use stereotype here in a non-negative or not judgmental way. You have this norm or this stereotype in your mind that you cite or you draw on, and you think of that as being typical of the class. So when things happen, or cues or hints or evidence mounts that starts to sort of point to that stereotype or point to that thing that you hold to be typical of the class, then your estimation of the probability that that person belongs in that class or is part of that base rate goes way up. Whether or not your actual sample or your stereotype is actually representative of the real phenomena in the world. Okay, so Kahneman and Tversky constructed this very carefully composed description of a guy named Tom W. And the description is designed to activate some of these stereotype expectations you have and throw you off from paying attention to base rates, and in a couple of famous studies they did with subjects. So Tom W. is of high intelligence, although lacking in true creativity. He has need for order and clarity and for neat and tidy systems in which every detail finds its appropriate place. His writing is rather dull and mechanical, occasionally enlivened by somewhat corny puns and flashes of imagination of the sci-fi type. He has a strong drive for competence. He seems to have little feel and little sympathy for other people and does not enjoy interacting with others. He's self-centered. He nonetheless has a deep moral sense. Okay, so what Kahneman and Tversky did is they gave this description to a bunch of subjects, a bunch of students, and then they gave them a whole bunch of different career categories, and they had them rank the career categories to say, which one of these professions or academic fields or career categories do you think Tom W. fits into? And because of the way they described it, it led people to put computer science or computer programmer first. They asked, which academic field is Tom in? And the keywords in that story lead people to put computer science first, even though the other fields like humanities and education have far more students. And so what happened was they had a long list, and I won't reproduce all of it for you, but they had a long list of all these different fields. And some of the fields were things like a big category, a conjoined category of humanities and education. And the base rates of computer scientists compared to some of these other larger fields is very low, but the description made people put Tom W. into the computer science category. So what Kahneman and Tversky decided was that the stereotype we have of this guy, this nerdy guy who tells corny puns and has a need for organization, which could fit lots of different people, right? It sounds like an astrology forecast. Well, but the activation of that stereotype fills in this picture. It tells a narrative, and it distorts our assessment of representativeness and base rates and makes us assign him to the computer scientist category. So I'm going to cite you, I'm going to point you to Kahneman's more detailed analysis of all that to see what's going on there. So again, the representativeness heuristic is that we think our subjective, anecdotal, causal story, small sample model of a category is representative of the actual category. So the net result of all this research ought to lead you to be more skeptical of your intuitions and more skeptical of your sort of first impressions when you want to give the answers to these questions. And the lesson here is that we shouldn't ignore the base rates, that in lots of these cases where you come up with a fast, quick answer to some question, you ought to ask yourself, okay, what's the base rates? Like, how common are computer scientists in the population versus some other property? And you'll see the same thing happens with Linda, the bank teller, in a minute. So humanities and education, which was one of the categories in this list that they gave to students, or social science and social work, are much larger base rates for Tom W. And I'm not given all that list there, but obviously, if you lump in all of the people who are in the humanities and education fields, of which there's a whole bunch, that's going to be a much wider class, a much bigger base rate than just computer scientists or social science and social work. Okay, that covers a whole bunch of different fields. And were you to think about the base rates, you realize, oh, whatever else is true about Tom, he's most likely to be in the largest category here, even though I'm, having this impulse to say he's a computer scientist because it fits so nicely. Okay, so we're at work. One of the things we're doing this semester is we're trying to discipline intuition. And one of the things that Kahneman tells us is that we should start learning and practicing and figuring out what does Bayes' theorem teach us. Now, Kahneman talks about it a little bit in the book, and this is a place where he mentions Bayes' theorem before we're getting to it in my class. So in my class, we're going to do 2 or 3 weeks of careful, detailed problems of solving problems with Bayes' theorem. So this is partly a promissory note for what we're going to do soon. We're going to do a lot of Bayes problems to improve and calibrate our ability to combine 2 probability classes. When you get these converging probabilities, how do you know how to discount one or how much to improve the weight or increase the weight of another? How do you combine them? And we're going to start looking at those cases. We'll look at a few today, but by and large, this is coming later. So our class will re-intersect with Bayes' theorem here in a couple of weeks. There's Bayes' theorem for 2 mutually exclusive hypotheses, and Kahneman doesn't talk about it because he keeps the book non-technical, but he says this. He says, you should learn to anchor your judgment of the probability of an outcome to a plausible base rate. And this is my point about social scientists or about people in the humanities. And the base rate is also known as the prior probability in Bayes' theorem. And Kahneman also says we should question the diagnosticity of your evidence. Now, the other technical name for this is the likelihood or the accuracy of the test, and those are right there in Bayes' theorem. So again, I'm just going to put this as a placeholder for what we're going to talk about later in my Bayes' theorem lectures. We're going to look at those 2 parts of the numerator. The one on the right is the prior probability. That is, what's the probability the hypothesis is true before I make my observation of the evidence? And the one on the left is how accurate or how good is the test or the measurement device I'm using to look into this question. And you're going to see when we start looking at pregnancy tests or COVID tests or eyewitness reliability and the like, that as you change these 2 numerators around and adjust them, you'll start seeing what happens to the answer, which is the solution on the left-hand side of the formula. Okay, so again, we'll get to more of these soon in my Bayes' theorem lectures. Okay, so here's another problem, famous problem that Kahneman and Tversky constructed. They gave this description about Linda, and you saw us talk about this in my lecture in the beginning of the course. They give this description. Linda is 31 years old, single, outspoken, and very bright. She majored in philosophy. As a student, she was deeply concerned with issues of discrimination and social justice, and she also participated in anti-nuclear demonstrations. And then they asked students to evaluate which of these is more likely about Linda, that she's a bank teller or that she's a bank teller who's active in the feminist movement. And this makes Kahneman's point really nicely. Because what happens is that lots and lots of people think that 2 is more likely than 1. The more we specify, and the problem is that that's a mistake statistically. The more we specify the details in a prediction, the more the probability must go down. And that's that probability rule that we've started to see play out in some of our probability calculations. Look, the probability that I'm going to flip a coin and get a heads once is 0.5. The probability I'm going to get a heads and a heads in 2 flips is 0.5 times 0.5, which is 0.25. I'm specifying the situation in more detail. I'm specifying more independent properties, and as those go down, what happens is you multiply those together, and the overall probability of this more specific story or this more specific prediction goes down and goes down. But we have counter intuitions about this when the story fits. When 2 fits so nicely with the description above, we discount the fact that the odds of her being both is lower than the odds of her being just 1. Nevertheless, majorities of subjects asked to judge they judge two to be more probable. And Kahneman calls this the conjunction fallacy. It's the mistake. It's the mistake of it's failing to see that when we specify a situation in more detail, the probability that it's all true goes down. Here's some more examples. Consider these. The way he puts it is very nice. When you specify a possible event in greater detail, you can only lower its probability. Which is more probable, that Mark has hair or Mark has blonde hair? Well, blonde hair is a smaller category than hair, so the latter is less probable. It's more probable he has hair, less probable he has blonde hair. Which is more probable, Jane is a teacher or Jane is a teacher who walks to work? Which is more probable, there is an earthquake along a fault in California or there's an earthquake somewhere in North America? So in these cases, what happens is, and I should reverse the third one to get them in line, is that the Mark has blonde hair evokes a vivid image. Jane is a teacher who walks to work invokes a sort of narrative story about her character. And the earthquake along a fault in California tells a story that's very vivid and very clear, especially to lots of us who live in California. It's not as powerful or as compelling as there's an earthquake somewhere in North America, which is vague and sort of open. But obviously, the probability of an earthquake somewhere in North America, which is vast, is much, much higher than an earthquake along a fault in California, which is part of North America. Same for the other cases, right? So specifying in more detail makes the probability go down. Causal narratives lead our systems to inflate probabilities of a good, detailed, vivid story that easily invokes our stereotype models. That really captures one of the main lessons of this section of Kahneman's book. And the recommendation again is that we shouldn't ignore base rates, we shouldn't ignore the class we're talking about, and the bigger point is that broader categories are more probable than detailed narrow categories. Okay, so here's another place where our thinking about statistics goes off the rails. Suppose you're looking at a set of dishes at a garage sale. I'll use one of his examples or one like it. I've got some more in our quizzes. And you're looking at 8 plates that are all in perfect shape, but there's also 4 saucers there that are chipped. So it's a complete set of 12 plates, 4 of which are damaged. Okay, so we ask you, how much would you pay for that? Or what's that worth to you? What would you give for the 12 plates, including the 4 chipped ones? And then suppose that we take somebody else, or you, and we have you just look at the 8 plates in good shape without the chipped ones present. So now imagine the difference here. Single evaluation in Kahneman's terms are, imagine that I have one person look at the 8 plus 4 plates, and I have another person look at the 8 plates only. So that's single evaluation. Now you're currently doing joint evaluation. You're considering both. You're considering the class of 12 and you're considering the class of 8. So you can see, and you would notice, that this is wrong-headed and weird. Which group will you pay more for? Now, if you ask people to answer this question singly, they'll give a really peculiar reply. When they're considering these cases separately, people say that the first batch is worth less than the second. That is, the first batch, that is the 8 good plates plus 4 chipped plates, they will say that that's worth less than if you just showed them the 8 good plates, the very same 8 good plates alone. Something weird's happened there because actually showing them more leads them to offer less. He calls this section less is more. Strangely enough, when you give people this broader category, this bigger set, they will devalue it. Something's happening here. What's happening? Well, it's those chipped plates that are added. When you add in those chipped plates, there's like a toxic influence. There's a kind of averaging or a kind of rubbing off of brokenness or devalue or something negative from the 4 saucers. The chipped saucers is rubbing off onto the 8 good plates. And I know about this example and I understand it and I can even feel it. Like there's something about looking at the 12 plates with the 4 chipped ones. The 4 chipped ones are going to bug me. They're going to bother me and make me sort of devalue the whole thing and discount it. But if I saw a sort of nice, clean, tidy set of 8 plates that are in good shape, I would sort of think of that as a kind of cohesive whole, a complete finished whole that has no damage. Now, when somebody looks at both of them, like you're currently looking at this option of 12 and 8 plates, people see that obviously the first one must be worth more, because whatever the second batch is worth, the first batch is worth that plus some more, whatever else you'd pay for some for additional chipped plates. So when considered jointly, that is when somebody considers both options right in front of them, they can see that 12 is more than 8. But when they consider them singly, they somehow think that 12 is worse or less than 8. That's the weird less is more phenomenon. Somehow the nice plates got pulled down, or they got influenced or rubbed off on by the chipped saucers. So that's another place where our intuitions and our systems lead us to struggle with thinking about statistics or thinking about probabilities clearly. That we have trouble sort of seeing this obvious relationship between these objects in front of us, and we get these screwy ideas about norms and representativeness. Okay, so here's another example, and again, this is going to be an allusion to Bayes' theorem, but Kahneman and Tversky constructed this example, and they asked a question. So imagine a cab is involved in a hit-and-run accident at night. There's two cab companies, the green and the blue, that operate in the city. 85% of the cabs are green and 15% of the cabs are blue. An eyewitness who we've tested, and we know the eyewitness is only 80% reliable, says that it was a blue cab. Question: what's the probability that it was a blue cab? Is it 80%? Is it 70%? Is it 40? Is it 10? What's the probability that it actually was a blue cab that was involved in the accident? Okay, now when you tell this problem this way, what happens is that people ignore the base rate. And what's the relevant base rate? That only 15% of the cabs are blue. So very few cabs are blue. The eyewitness in this case is testifying to something that goes contrary to the trend in the base rate. That is the distribution. There's a heavy bias in the population in favor of green cabs against blue cabs, and the eyewitness is saying that's a blue cab. So we tend to go with the eyewitness for a bunch of reasons here, and we tend to answer or inflate or elevate this situation. The way this problem is described increases our estimation that the cab was actually blue, when in fact you have to use Bayes' theorem to get the right answer, and the correct answer is actually 41%. Most people ignore the base rate and go with the eyewitness, and they'll say something around 80%. So they'll discount or I guess that they put it close to what the eyewitness said, or close to the eyewitness's reliability. That is, they tend to disregard the base rate and just go with however good or however confident the eyewitness is, we just settle with that. When in fact, when you combine this 80% reliability from the eyewitness with the 15% base rate, that brings that number in between those two. So we get some number between 80 and 15, and that turns out to be 40 according to Bayes' theorem. And there's examples like this in our homework assignments. There's examples like this in our quizzes for the class, and I've talked about this example at the beginning of the course. So here's the interesting thing that happens, is you can actually use people's causal thinking to improve their performance on a problem like this. So if we change the story and we tell it this way, if we say something like, green cabs are involved in 85% of the accidents. So now what I'm doing is I'm telling a causal story that green cabs cause 85% of the accidents, or something like that, right? They're involved in, or that I'm attaching 85% of the accidents to the green cabs. Telling the causal story gets them to give more weight to the big base rate. And what happens is that their performance on this question improves, and they start doing better. Like they go, well, the eyewitness is pretty reliable, and the eyewitness says a blue cab, but green cabs are causing or involved in by far the vast majority of the accidents. So they discount, in their thinking apparently, they discount the eyewitness's reliability and the strength of that answer as they should, and they get closer to the right answer. Okay, so that's a way to actually use this sort of, if you like, think of it as we were treating it as a bug before, and now we're treating it as a feature. Here's a way to get you to improve your performance on some of these problems, is if you can put the thing into the right kind of causal form, your answers will come out better if you've incorporated the base rate into your thinking. Okay, so statistical base rates are often ignored or underweighted. Causal base rates work better for us and improve our predictions, is what we learned just now. And again, in Kahneman's usage, and there's some discussion for a couple chapters on this, he's using this term stereotype. Now, you will no doubt think of the term stereotype in almost entirely a negative way. When somebody says, oh, well, you're stereotyping Mexicans, or you're stereotyping African Americans, or you're stereotyping women, that all conjures up negative comments or bad prejudicial ideas or bias against them. Okay, well, that may be true, that those are vicious stereotypes that people have about those groups, but think about the broader notion of a stereotype. It's where you're using a model, an idea that you've got that you think of as being the norm or being a prototypical exemplar of a class. So what's happening is not just the fact that somebody's using a stereotype to talk about Mexicans, but they're using a stereotype that includes some of these really negative characterizations. We all use stereotypes more generally. That is, we use an item or a typical instance to represent a class. And what's being protested in the case of like a racist stereotype is the particular details of that stereotype in that case on the basis of race. Okay, so Kahneman's using stereotype and the idea of norms here in a neutral way. And we all use them to think about all kinds of categories like horses or New York cops or whatever. You've got, just by saying that, I've invoked an idea in your head about what a New York cop is. You've got it from movies and experience and television shows and like you've got an object, a person in mind that stands for what a New York cop is. And were you to find out that somebody was a New York cop who really violates those expectations, you'd be sort of surprised, because that stereotype represents the model for you, and the extent to which some real example deviates from that model is the extent to which you're going to be surprised about it. So we use those all the time for lots of cases. And that's partly what's happening here with the statistics, is that your stereotype may or may not line up with or match to the base rates or match to the actual properties of these things in the population we're considering. We do poorly with statistical information, but when we cast it as a causal story, we can model and predict better. And that was the example from the previous case with cabs, for example, for one of the cases. Okay, so let me show you another place where we go off the rails, and this one might be familiar to lots of you. And Kahneman spends a couple chapters talking about regression to the mean. So let's figure out what that is. There's a widespread view among sports fans that if a star gets on the cover of that year's edition of the Madden football game, it's a video game that gets issued every year, and a different famous football player will be on it every year. Or if some sports star gets on the cover of Sports Illustrated, the belief or the urban mythology is that that star will be cursed and their performance will slump right after that, and they'll get injured or they will lose or something bad's going to happen to them. And if you haven't heard of it, go look it up. It's called the Sports Illustrated cover jinx, or the Madden football jinx or curse. And there's lots of people who believe in it, and lots of people who cite examples. They will point to that cover, and I don't know anything about Murphy or whoever that is, or the cover of the football player, and actually those are held up as examples where something bad happened, or that sports star's performance slumped right after they got famous and got on the cover of the video game or of the magazine. And people what happens is that people get the causal arrow mixed up here about what's causing what. And I'm using this example, I think Kahneman just mentions it briefly. I'm using the sports examples because it really illustrates this regression to the mean problem that people have. What's happening is we're misunderstanding statistics again. And here's why. We're getting it all backward when we do this. So think about this for a second. What gets you onto the cover of Madden football game or Sports Illustrated? What makes a star famous and gets them attention? Well, it's a bunch of wins. It's a bunch of successes. It's a great season or an unusually good series of performances. The athletes that get noticed are the ones who are doing great. And then Sports Illustrated says, well, who should we put on the cover this month? Well, who's been really excelling? And they put them on the cover. Okay, so that's those red arrows on that deviating athletic performance over time chart I've got there, is that those peaks, those wins, those shutout pitched games, those track meets, whatever it might be. Those catch people's attention and get you on the cover of Sports Illustrated. But now here's another question. What's the normal cycle for an athletic performance, or for any system that has complicated subsystems, elements of randomness, and that needs a lot of things to go well for it to succeed? What's the normal course of events? Leave the Madden cover or Sports Illustrated out of it. What's an athlete's performance going to do over the course of a year or 3 years or 5 years anyway? A normal athlete's performance is going to go up and down. It's going to have peaks and troughs because there's a lot that goes into it. You have to get your sleep right, your training right, your diet right. You have to be injury free. You have to have a lot of luck. A lot of good things have to happen for you and line up for you. A lot of things have to come together for you to have that stellar performance where you exceed expectations, or you set personal bests, or you achieve these personal records, or your highest weight lift ever, or whatever. A lot of things have to go right for that, and if any one of them goes wrong, it tends to push your performance back down towards the mean, back towards toward the middle. What happens to the normal cycle for athletic performance, or for just about anything that matter where it's complicated, where the correlation is not equal to 1, as Kahneman says, is that the performance will regress to the mean. So the point is that it would have happened anyway. This athlete's performance was going to go down there and plummet. It was going to trough out at the end of the season or halfway through the season anyway. But that's not a curse. That's not because, see, look, this guy got on the Sports Illustrated cover right here because he had this string of wins. But the normal thing to do would be then to have a trough thereafter. But people cite Sports Illustrated or the Madden cover as being the cause of them going downhill. Well, they would have gone downhill anyway. That's what happens over the normal course of things. So there's no curse here. There's no jinx. It's a confusion about about causes and statistical errors. Okay, and we shouldn't underestimate the role of luck here. We attribute much of our success to skill, hard work, preparation, talent. You ask any of those athletes in the debrief after the big game, how did this all come together for you? And they'll say all of that stuff, but nobody says much about luck. We discount how large the role of luck is in our successes and our failure. And in our failures, we tend to think that something causal was going on there when it turns out that just a lot of it was luck. And some bad luck can wreck your performance, and some good luck can really send it soaring, and it may not have anything to do with the variables or factors you thought it did. Think about it this way. How hard is it to have some good luck and golf above average on one day versus how hard is it to have good luck all season long and golf above average in a dozen tournaments? The latter is much harder, right? So probabilistically, the former is easy to happen or can happen. Probabilistically, the latter doesn't happen very often. It's much harder. It's much less likely just because of the variations in the phenomena. The latter is much less likely to happen. It's unstable, and the system will inevitably regress to the mean or go back to a closer to average performance. So very often, there's just nothing here that needs to be explained, even though we think there's some cause that must account for it. So here's some more examples. Why do highly intelligent women tend to marry men who are less intelligent than they are? And that question by itself is very suggestive to you. And you're spinning through causal explanations right now about how maybe she doesn't want to feel threatened by her man's intelligence, or the man's impressed by her intelligence, or whatever. Why do short men tend to marry women that are taller than them? And the way I ask the question is going to make you come up with a story that explains what the cause is. Why do people who are successful in business tend to have friends who are not as successful? And that suggests a kind of psychological explanation account. Why do depressed children who drink an energy drink tend to improve over 3 months? And that really suggests a causal story that the energy drink is helping their depression. But the answer in all these cases is not the causal story that you think. The answer is that because outliers swing back to the mean. The answer is regression to the mean. There's no cause that's needed in these cases. Resist the causal story in every one of these cases. Regression to the mean is the only explanation that's needed. Okay, so the last section here is about taming our non-regressive intuitions. So regression to the mean is the phenomenon we were just talking about. And what happens is that you have intuitions that swing wildly away from the regression to the mean. You have non-regressive intuitions. You tend to think of or expect sort of outlier performance from yourself or from your sports star every single time. So Kahneman and Tversky gave this famous example. They gave subjects this example to think about. They said, Julia is currently a senior in a state university. She read fluently when she was 4 years old. What is her grade point average now that she's a senior in college? And just given that one tiny piece of information about her reading fluently when she was 4 years old led people to make a very high prediction. They would answer something in the order of 3.7 to 3.8, around, you know, a high B to A average for Julia, because she's a precocious reader, and at 4 years old, that seems to be a real good indicator of how smart she is, because those two fit together and they tell a story and they project a sort of optimal outcome here for Julia. But that's wrong for a bunch of reasons. The story and our causal narrative impulse leads us to assume that our knowledge is more predictive than it is. You don't know anything about Julia except that she read when she was 4, and there's so much that could happen between her then and her at 22, and that the information is more relevant than it is, and we confidently conclude that this fact from when she was 4 informs us about her at 22. Since that's the only information we were given, and Kahneman talks about this, what you see is all there is. That's all you can think about with Julia, is that she's at university and she was a really precocious early reader at 4. So we tend to think of, well, that makes Julia a super smart, high accomplishing student, right? So the thing just locks together and fits nicely for us. So what Kahneman talks about, and he's got a very detailed and interesting discussion that I'm going to point you to in the book, is he talks about the way that norms, the WYSIATI, what you see is all there is, the way the causal narrative, the way substitution and intensity matching all lead us astray on this, because we shouldn't predict that Julia's grade point average is so high in this case. We should assume more regression to the mean. What you do in this kind of case, just to give a really quick summary of what Kahneman says, is that you picture the best possible scenario for Julia without thinking about regression, without thinking about the strength of the correlation between reading at 4 and GPA in college, which there's a lot that goes on between those two. There's not a very good correlation there. The quality of the evidence and so on. And what you should do here is moderate. You're coming in with a high number, and you should moderate and tame it and bring it down closer to the mean. Okay, so again, read that section carefully and take careful notes, because Kahneman's got a lot of important detail there that I'm just glossing over quickly here. Okay, so now we're at the end of the second part of this set of lectures about chapters 10 through 18. We've talked about stereotypes and representativeness and base rates. We've talked about the conjunction fallacy, which you should understand and be able to catch and see in these cases. We've talked about single and joint evaluations, and that's the case of the plates, of 8 plates and 4 plates versus 8 plates, and chipped and perfect plates, and the way that averages and sort of poisons our view about the other good plates. We've talked about causal stereotypes and the way they mislead us with statistics, and then we've talked about regression to the mean, and we've talked about taming intuitive predictions. All right, so that's the end of our discussions of Kahneman 10 through 18.